Well, hello there. So let's talk about the compass and this particular compass we're using for our class, the MPU 9250. Okay, so the compass is a sensor that measures the direction of the Earth's magnetic field. So the Earth has a magnetic field that goes through the pole, and the magnetic field lines come out in these circular patterns. They radiate out and around. And so the North Pole of the magnetic field is pretty close to the Earth's North Pole. And so that's what we use for compass directions. It's important to realize when you look at this picture, we're up here somewhere in the middle latitudes. And if you zoom in on that, you can see that the field as it goes through the surface of the Earth has a pretty big vertical component. It's not horizontal, it's not parallel to the surface. It actually goes in, and that Z component is pretty strong. It's one of the bigger components. So what this means is to do compass in general, you need a 3-axis sensor, and you need to get the horizontal components of that vector. What we're going to do is we're going to hold our compass flat and assume that that is horizontal. But the way we're going to do it is very sensitive to tilt. So if your robot goes up a hill or tilts, our method that we're going to look at here won't work, and you need to do something more complicated, which involves knowing the angle of tilt and backing out the horizontal component. So we're not going to take that step, but that's what you would have to do. The other thing is that the Earth's magnetic field is very weak. So compasses are really pretty terrible sensors. It's very hard to get a good compass reading if you have an electric motor nearby, if you have big power cables nearby. If you happen to live on the ship that's made of steel, your compass won't work at all. If you're in a classroom with steel desks, all of these things make the compass really not work well. So your best bet with the compass is to be outside at a wooden table. That's where it's going to work the best. Everywhere else, you may have troubles. So definitely keep that in mind when you're running your robot. And test your compass. Take a skeptical look at it. Really make sure it's working. Don't just trust the sensor, because the sensor is not trustworthy. Compass heading is the direction measured from north. It's measured clockwise. So east is 90, south is 180, west is 270 or minus 90, sometimes people would call it, and north is 0 or 360. So keep that in mind. It's different from other angles in geometry. We would normally measure counterclockwise positive, and we normally measure from the x-axis. With a compass, for traditional reasons, we measure from the y-axis, and clockwise is positive. When we have a magnetic sensor on our robot, this is a little picture of a robot with a sensor. Here's our magnetic field that's being measured. And it's measured in the axes, the body axes of the robot, so that X is facing forward on a robot and Y is facing this way. And so this magnetic field vector is measured in its components, in the components of the robot. So if we need to know the heading is this angle. Usually psi is traditional for a heading angle. And you can see from the triangle that the tangent of psi is the y component over the x component. So we can calculate psi using the arctangent function of y over x, those two components. So if we get these from our sensor, we can calculate the heading as an angle. When you're doing this in your code, you have to be very careful with arctangent. The atan function is there, but you really need to use a function called atan2. It's also going to be in C and Python and MATLAB and Fortran. Everybody has atan2. So arctangent 2 will let you differentiate between -1 divided by 1 and 1 divided by -1. Those are in different quadrants of the unit circle. But if you just use the regular arctangent, they'll both be -1, because -1 over 1 or 1 over -1 evaluates to 1. So you need the arctangent 2 function to make this work. So you'll see some examples, and I'm always going to be using atan2 to evaluate this angle. The other thing with angles is that if you can add 360 degrees to any angle, and it's the same angle because you just are going around more than once. So whenever you're doing math with angles, like compass angles, if you're calculating things like error, compass error, and subtracting angles, or even just getting the angle from your compass, you can always add and subtract 360 degrees, and this can make a big difference in things like feedback control, where we're calculating an error. If your error is 360 degrees bigger than the equivalent angle, it's a very big difference in terms of the math. So the convention normally is to wrap our angles so that they're in the range of plus or minus 180 degrees. That way, 0 is the middle, and you can go 180 degrees one way and negative 180 degrees the other way, and that will make things sort of symmetric in the math operations at least. So anytime you calculate an angle, you should do these two steps. The first one is divide it by 360 and take the remainder. That way, if you're like 10,000 or something like that, if you have some crazy large angle, then you can't just subtract one 360, you have to subtract it several times. So F mod in C or mod in MATLAB is the modulo, and it'll take it the remainder. This will make your number between 0 and 360, positive 360, negative 360 maybe, I can't remember. But then you have to do one more correction. If it's less than negative 180, you add 360. If it's greater than 180, you subtract 360. And this will limit us to plus or minus 180 degrees. So always do these two things, these two tests for the wraparound. A lot of times you can get away with skipping the F mod part because if you don't get really huge angles, it'll be fine. If you're doing some sort of integral control or summing angles over time, then you definitely want to use this. But you have to use this every time or you'll go the wrong way. Negative 90 and 270 are the same angle, but one involves turning, one's positive and one's negative, so you'll turn the wrong way with a lot of control schemes if you don't do this wraparound. The other thing your compass is going to give you is the magnetic heading, which isn't quite the same as the true north heading, and it depends on where you are. In some places they line up, but most places have declination error, and it's location dependent. So there's a website here that you can go and find at Cal Maritime. We have about 14, actually about 13 degrees now. I just checked it. This was in 2016, and it's decreasing every year. So, but anyway, if you're within a degree, you're doing great. So to find the true heading, you take the magnetic heading and add 14 degrees, and then again you're doing math, so you have to then wrap it around, because if your magnetic heading was 359 and you added 14, then you've wrapped around. Okay, so that's the basics of how compasses work, and it's really important to remember not to trust your compass, to check your compass all the time and be skeptical of the results until you can really strongly verify them. This is the Invensense NPU9250 that we're using, this little chip. For our class, you probably bought it on one or the other of these boards. This is the High Let Go, and this is the Spark Fun version of boards that use this chip. This chip is really great. It actually has a lot more than a compass. It has a 3-axis gyroscope, so it will give you not degrees, but degrees per second. So your turn rate in X, Y, and Z, all 3 axes. It has a 3-axis accelerometer, so it will measure your acceleration in G's. It also can be used for measuring tilt if you're not moving. And the 3-axis magnetometer. So we have all of these 9 axes of measurements, and we're going to use 2 of them for our class. But it's a nice chip, so sometimes people want to do these if they want to make pendulums and other kinds of drones and crazy things. So it's a nice sensor to have around. It has an I2C interface, so the wiring is pretty straightforward, and there's a nice library for Arduino that we'll see. So you need 4 wires to the board, even though there are a lot more pins. You really only need these first 4 pins here. So you need to give it power. The blue ones, these High Let Go ones, they have a voltage regulator. This is a 3.3 volt chip, and if you power the chip with 5 volts, you'll damage it. So this one has a 5 volt regulator, so you can put 5 volts into the VCC. If you have the red Spark Fun board, it doesn't have a regulator, and you have to use the 3.3 volt supply on your Arduino to power it. If you power it with 5 volts, even for a second, you'll probably break it and it won't work anymore. So be very careful if you have the red boards. So you need power. Everything always needs a common ground, and then you have the two I2C connections that we talked about in the serial lecture. SDA goes to Arduino A4, A4 not digital 4, and SCL as the clock goes to Arduino A5. This is for the Arduino Uno or the Nano. Both use these. Remember, I2C needs a pull-up on the data line, the SDA line, so that it knows when the chip's available. But both of these boards include the pull-ups on the board, so you don't need to add them. And then the other connections are for fancier ways to use the chip than we need. So here you can see I've mounted this board on my robot, and I've got an Arduino Uno. So there are 4 wires coming from the board down to the Arduino board. It's important to keep this away from your motors, especially the 4-wheel drive have 4 motors with decent magnetic fields. So if you mount your compass right down here at the level of the top of this platform, it's too close to the motors. You won't see that. You won't be able to tell that you're moving, because all it's going to measure is this fixed magnetic field that's moving with the robot. And even worse, when you run the motors, you'll get a different magnetic field, so it will do weird feedback. And you'll see in the calibration that it just you can't get a reliable number. When you calibrate it, it still won't work. So moving it away, this is farther than you need to move away, but lifting it up is usually the answer. So put it on top of a cardboard box, or a coffee cup turned upside down, or something like that, chopstick. Lift it away from your motors. You probably only need to go, 6 inches or so would be plenty. You might do less if you calibrate it carefully and then look at it critically to make sure it's working. Okay, so to use the sensor, we are going to use, there are several libraries for this chip, and we're going to use the one by Asukia, because it's a good one that just does the basics. It reads the components of the magnetic field. It doesn't try to do a bunch of synthesis and more complicated things. So some of these other ones are fancier, but they take a lot of processing of power away, and we're not going to, we just want to look at the 2 magnetic field components. So I like this one. You can get it using the library manager directly in Arduino, and just click install and it'll install it for you. So to talk to the sensor, in the setup you have to declare an instance of the library. So this is the library's class name, MPU9250 Asukia, and I'm calling it my sensor because I'm following the example that was part of this library. And so this is my instance of this class. And then in the setup function, I'll set up the normal things like the serial port, but then I will start reading all of the axes. So my sensor.begin, accel, gyro, and mag. You really only need mag. I've also declared some variables to store the X, Y, and Z components of acceleration, gyro, and magnetic field. Then in your main loop, what you do is you call this mySensor.mag update, and there's an equivalent one for the gyros and accelerometer updates. And this is a function that talks to the sensor and reads all the components. And if it works, it returns 0. And so this calls the function and checks that it works. And if all of that happens, then you've got new numbers that you can read using the .magx, mag-y, and mag-z functions. They'll return the components. So this is how we do it. We tell it to talk to the compass, and then we pull these out of the class. And here we're just printing them out to the serial port. If you want to do the angle, the heading angle, it will look something like this. You'll have the A tan 2, the X and the Y components. The minus sign here is because arctangent is positive in the counterclockwise direction versus clockwise for the compass heading. And then the minus sign here and the order of X versus Y depends on which way you mount the chip on your robot. So you'll have to face one of the axes forward, and so there's some comments in the example code, but sometimes you just flip these around until it all looks good. again, taking a close look at your calibration values. And arctangent 2 gives answers in radians, so here we're converting to degrees. And that's all there is to using it. We call these functions, and then we can do the math, and we know our heading. Before you can get good numbers, though, you have to calibrate your compass. You probably only have to calibrate it once, and then you can use those offsets until you change chips, or if you reinstall it in a different vehicle with a different magnetic field. The reason we do calibration is because there's a magnetic field attached to your robot that you're also going to measure, and we want to subtract that out. And what the effect of the extra magnetic field is that if you rotate around and plotted x versus y, we get this nice circle, and the angle, the heading, is based on the x versus y, but you can see the center of the circle is not at the origin, and that's what we have to do. We have to add a constant to the x and y components to move this center back to the origin. Otherwise, when we do the arctangent, it's based on here, and so we'll use this angle from the origin to the points rather than the center of the circle to the points. Sometimes this comes out like an ellipse, and then you have to actually scale the axes, but in my experience, just the offset gives you enough to work as well as the compass ever works anyway. So how do we do it? This is what we do to calibrate it. We just spin the robot around. So we rotate the compass, mount it on the robot, and we write down the maximum and the minimum values in both x and y. So here are the y components. When the y is maximum, we should be facing north. When the x is maximum, we should be facing east, and west is the opposite. And then if we have the right center here, when we're facing north, the y is at a maximum and the x should be at 0. Up here, this should be x of 0. So those are the things to check. So we write down the maximum x's and the minimum x's and the maximum y's and the minimum y's as we spin around. So you spin around several times, and you can have the code record the maximum. I'll show you that. Make sure when you're running calibration code that you didn't already have calibration constants, because that's a very common error to do. Make sure they're set to 0. There are comments that you can read. Then we subtract the average, x max plus min divided by 2, from the x reading. So if we take the max and the min, the average is going to be in the middle, and we subtract that from everything to shift ourselves over just the right amount. And we do the same thing for the y. Then you check it, and you check it carefully. Don't just say, it gave me an angle. Make sure it's the right angle. So face north, face south, face east, face west, facing the cardinal directions, north, south, east, and west. You should have one of the components very close to 0. Probably not exact, but pretty close to 0. Then try northeast and northwest and all of the intermediate directions too, to make sure that things look pretty good. You're going to want to line up the compass on your phone using a compass app or an actual magnetic compass if you're a Boy Scout to the compass on your robot, and really closely make sure they're working. Make sure you're at a wooden table outside. You're not near any metal when you're doing the calibration and checking. The other thing I see students do sometimes is they just wire up their compass and they let it dangle on some floppy wires. That's going to give you the angle of the compass flopping around, not the actual robot. So the compass should be mounted flat to the robot and not and rigid, so that when the robot turns, the compass turns, or else you'll get really weird feedback. Okay, so next up I will do a compass calibration. I'll show you the code and I'll walk you through this spinning it around and where to put the constants. Okay, so here you can see I've got my robot set up and I've got the calibration software loaded. So this has some good instructions on how to set this up. The important things are, when you're calibrating, make sure that your offsets, they're part of the library, are set to 0. So make sure you do that very first, or else you'll get garbage calibration. And then again, you can't trust the heading until you put actual calibration numbers here. So we'll look at those two things as we go through this. And you can see we're including this instance of the library, and we've got the initialization happening here for the magnetic components. So down here in the loop function, we're just reading the magnetic components, x, y, and z. And then there's a little test that if the x component is greater than the maximum that we've ever read, we save the x component as the current maximum. And if it's less than the minimum, we save the minimum. So we're looking for new biggest values in x and y, and we're saving them here. So this is what we would normally just watch and write it down by hand. It goes pretty fast. But this way the computer watches and writes it down for us. And then it's using those to calculate the offset using the equation from the slides. And then here we're calculating the heading, and it prints all of this out in one big long line of numbers. I'm going to put that in my Arduino. Remember to make sure your offsets are 0 initially, and then I'm going to open up the serial port, bring it over here. So here is my serial port, and you can see I've got quite a bit of numbers going on here, and these are the x, y, and z components. Here's the maximum and the minimum, or the maximum of x and the maximum of y and the minimum of x and the minimum of y. And then this heading is garbage because we haven't calibrated anything yet, so we don't want to trust that yet, but we'll look at that later. And these are the offsets calculated using the current maximum and minimum. Right now my robot is facing roughly east, so about 90 degrees as my house faces north-south. This is out the side. So we can see we've got an x value of 46 and a y value of 105. And as I change it, my y is getting smaller, my x is also getting smaller, my y is getting bigger. I'm rotating it around, watching these values here. Now my x is negative, my y is getting large again. And as I spin it around, I'm trying to keep it flat. I'm on a wooden desk. Slowly spinning around. If you tilt this, you'll throw everything off, so make sure it's perfectly flat. I'm going to go around. Now I've done a whole circle and my cable's wrapped around, so I'm going to go back and rotate back the other way. See if anything changes. And so now if you watch these, if they stop changing, then you've probably already hit the maximums and the minimums. So we'll try that. So now my x offset, I'm looking at negative 13, my y offset about negative 95. So let's put those in and we'll see what happens. So then I go into here, x offset was, I already forgot, offset negative, we'll call it negative 14. And the y, negative 95. Pretty sure these are supposed to be integers. So we'll put those in, and then I'll reprogram it. And now, if everything works, we can check for the maximums and the minimums. So let's see. So now when I'm facing about east now, so I'm going to watch. I want this one to be the maximum and this one to be close to 0. So somewhere around here, yeah, you can see y, that's about 0 for y. So that's my, 15 degrees. I should really check it against my phone or some other compass. Let's see if I have a compass. Well, let's check the other axes. So if I go 90 degrees to there, about here or so, now my x has gone to pretty close to 0. That's good. If I go out here about another 90 degrees, my y is again close to 0. You can see it's not constant, but popping around pretty close. And here, my x, I can move it around until the x is pretty close to 0 too. We'll call that good enough. And then over here is the heading. So if I face it, this should be pretty close to north at my house. And I can adjust it till it's right about 0. And verify that it's north. Let me go find a compass. All right, Alright, so here's a compass that I got a long time ago at a home decoration store or something. So let me line up compass. The compass needle. It's not damped or anything. It's not an oil-filled compass. It's very much a compass for looks, but it does look nice. So we'll let it settle out here. I think I've got it about facing north, maybe a little bit more like this. So if I line that up, you can see my heading on the screen is about 0. If I turn it this way, it should be about west. Minus 90 is west, so if I line it up with minus 90, plausibly parallel. If I line it up here so that we're at 180 or positive or negative 180, right about there, looks like south. And again, west, I'll line it up to be 90. And yeah, it looks pretty good. So I would say this is working. You can get an app for your phone if you don't have a big old desk compass like this one, but this is fun for the video. So now my compass is calibrated, and I want to keep these numbers for all of my compass calibrations going forward. And unless I rebuild my robot or I burn out my chip and have to replace it with a different one, they should be good to keep going with these offsets. So you don't have to calibrate it every time. It seems to, I think in my experience, they hold true for quite a long time. All right, so give it a try and let me know if you need any help, but that should give you enough info to get your compass working.